Alright, it is 9 o'clock. I am going to get started. And I'm going to get started with the lab yesterday. So let me read Catherine's comment first. For each problem, I would like to understand why we are doing it, okay? And the mathematical approach, okay, I got that. Alright, so let's go ahead and get started with the lab, which is floating point 2. Alright, so there we go. Alright, so for question number 1, question number 1 is asking, in one step of base 10 scientific notation to base 2 scientific notation conversion, we need to make numbers in base 2 as large as possible before division by 10. So this has to do with, you read the notes, it's a little bit it's a little bit forward compared to where we are in that note. So it has to do with minimizing errors. In order to do that, we have to maximize the numerator in the division, or we have to maximize the dividend in the division to minimize the error. So part of the instructions of the lab is actually an explanation of why this is actually relevant. And then so the key of this particular question is we have an integer. Okay, so Catherine is saying that having trouble understanding the notes because of the lack of familiarity with the mathematical notations. Okay, all right. So we'll get back to that when we get to the class notes. But for now, we'll kind of stick with the lab. And the lab is asking, okay, so in order to maximize, so we have to kind of figure out how big we can make the dividend before we perform the division. And the math involved in this particular question is to ask basically how many times can we shift x, bit shift x, all to the left hand side before we run out of bits in a 64-bit integer. 2 to the power of 64 minus 1 is the largest value as an unsigned largest value that we can represent using a 64-bit integer. And bit shifting, each bit shift is basically multiplying x by 2, which means if we are shifting by p times, then we are multiplying 2 to the power of p to x. Okay, x can be the original bit pattern, and we just basically shift zeros from the right hand side, and therefore shifting all the rest of the bit pattern to the left hand side. And this plus 5 here is needed because in order to do rounding, we add 5 before we divide by 2, and that's why we have a plus 5 here. So the plus 5 has to be on the left hand side of the comparison, because we don't want the left hand side itself to exceed what a 64-bit integer can represent. So that's the rationale of having this question to begin with. And then for this specific version, and I cannot even remember how many versions I have in this particular exam, in this particular lab. So in this particular case, x starts with a value of 547,706. So the question now is, how many can I shift x to the left, or multiplying by 2, so either way is fine, okay? And don't forget the plus 5 before we run out of basically we run out of room for a 64-bit integer. So there are different ways to do this particular question. One way is to use a spreadsheet and just kind of go over all the possible p's starting from 0 and test each one to see whether it is exceeding the range that we are allowed to use. So that's one way to do it. The second way is mathematically to solve the equation or inequality in this case, using a calculator that can do log. So both methods are fine. I don't really restrict people of how to do this one because I just want people to have a general sense of what the main instruction of the module is trying to talk about. All right, so so I'll do it in both ways, okay, just so that this way we understand both methods. So I'm going to start with a spreadsheet method first, and you can use just about any spreadsheet program you want. Microsoft Excel works, Google Sheet works too, and I'm using LibreOffice, just because I'm using a Linux box here, and LibreOffice is very easy to install and utilize in Linux. All right, so what we'll do is we have a value for P, okay, and I'll just kind of copy the value from the question itself. So in the question we have 5. Okay, I think I can just copy and paste this. Okay, here we copy and we have paste. There we go. All right, so we got P itself, and then this is not P. This is X. Okay, so there we go. We got X, and now we want to look at different values of P. So the column A would be the values of P, and we can start with 0, and the next row is whatever the previous row, which is, this is how we can refer to the previous row, plus 1. So this way, I can just kind of copy this cell all the way down, and you will see how it is super convenient to do this when we get when we get the formula formulated. Okay, so over here we have the expression. So this is x times p to the power of 2 to the power p plus 5. There we go. So to translate that into equations in a spreadsheet, we can refer to this cell times, using power, 2 to the power of p. Oh, okay, I made a mistake here. Okay, so we have to first refer to x first. There we go. This is x times 2 to the power of p, which is this value over here, and then the plus 5. The plus 5 for the most part is not going to be affecting much, because I don't really use values that are right there, right at the border of overflowing. So the plus 5, typically does not do a whole lot, but in very few occasions, that does matter. So there's one more thing we have to do here, because I don't want to, when I copy the formula, I don't want the row number to change, so I have to put a $sign with the row number corresponding to x, because if I don't do that, that will basically be a relative one. So when I copy and paste it, it's not going to work. So now to copy and paste, we can use this method. There we go. So now I can just go ahead and do something like this. Okay, and I know that by row 64 we would have overflown already. So the question is, when is it going to overflow? You can kind of scan it and look at these values on column B to find out which one is greater than or equal to 2 to the power of 64 minus 1. But we can actually do something like even better. Okay, so what we can do is now we can refer to the value in column B, and then we just say, is it greater than or equal to 2 to the power of 64 minus 1. So you can just type a inequality in a spreadsheet, and it will just return whether it's true or false. So we want to keep going until it is true. So yeah, so we got quite a few extra items here, because it turns true when we get to this particular point, and we want to use the value right before. So this is so the correct answer is 44, because when p is 44, we basically maximized the expression x times 2 to the power of p plus 5, and if I bump it up by 1, then we would have exceeded what a 64-bit number can represent. So the correct answer is 44. That's one way to do it. So I'm going to show you the other way once I put this down here. Okay, so we got 44. The other way to solve this problem is to use basically just math. And to show you the algebra of doing that, I can use Zerno. And if someone can remind me, I can share the Zerno file at the end of today's lecture too. So this way you also get a copy of this stuff here. Let's start a new page. All right. So let me just write down the equation first. The equation is we want x times 2 to the power of p plus 5 to be less than or equal to 2 to the power of 64 minus 1. Now this part here is really just the largest value that an unsigned 64-bit integer can represent. This is where we start. Okay, this is basically a smaller value that we put into a 64-bit unsigned integer, but we want to maximize that value until before we do a plus 5 and the division by 2. So using algebra, we can take away the same amount from both sides. So I can now say this side is x times 2 to the power of p, and then I will subtract 5 from both sides. Then the other side becomes 2 to the power of 64 minus 6. And now, because I want to solve for p, because x is already given, so now I can say 2 to the power of p is less than or equal to, and now we can say 2 to the power of 64 minus 6, and I'm dividing both sides by x. So if I divide the left-hand side by x, x divided by x is cancelled out, it becomes a 1, and on the right-hand side, I would just have a division by x. So now we are almost done. Because I can take the log 2 of both sides at this point. So now I can say log 2 of 2 to the power of p is less than or equal to the log 2 of the whole thing over here. 2 to the power of 64 minus 6, and then the whole thing divided by x, like so. And now, because the log 2 of 2 to the power of something is just that something, because log 2 and 2 to the power of, they cancel each other. They are inverse functions of each other. So now we have p being less than or equal to this entire expression here, because that's just moves down here. So that's going to give you a value that is not an integer. We just have to find the floor of that particular value, which is the largest integer that is less than or equal to the value itself, and that becomes the answer as well. Alright, so let's check whether this method works. Okay, so what we'll do is I'm moving Zerno out of the screen, out of your screen area just a little bit so I can see it while I enter the equation into the spreadsheet. So now we just put it, let's say, over here. So this is a direct answer. Okay, it is not by testing. Now the testing approach is actually useful as well, because it shows how you can do this using an algorithm. Okay, without using the actual log function, we can do it this way. So we'll go ahead and enter the equation. So p is going to be the log 2. So in LibreOffice log can specify a base, which is really handy. So if you specify a base of 2, then it becomes a log 2. So now we specify what goes in the inside of this. So we got 2 to the power of 64, the whole thing minus 6, and then divided by the constant that we have, which is x, and I can just refer to b1 in this case, and it gives us 44.93 blah blah blah, and the floor of this is just 44. So if I want to take this one more step, okay, I can take the floor of this value, it is just 44. So both methods will get us to the same answer. One is more of a programmatic or algorithmic way to do it, which is just by testing it. And then the other method is more of a math method by solving this inequality using algebra. So do we have any questions about question 1 in the lab? Question 5 is just another version of the same kind of question. All right. So what does the 44 tell us? So 44 is how many times we need to shift x to the left hand side, or how many times we have to do a left shift before we maximize what a 64-bit integer can represent. And each time we shift, we have to make an adjustment to the exponent of 2, so that the number of times we are shifting is how we adjust the exponent of 2, so that we end up still representing the same value. Is that okay? I mean, we have to count it, because we have to count the number of times we left shift, because we have to make up for the left shift operation. When we left shift the mantissa, we are doubling the value of the mantissa, but that will also change the value that the whole thing is representing. So by adjusting the exponent, by decreasing the exponent by 1 every time we left shift the mantissa, we maintain the value that is being represented, but we are also preparing ourselves for a division by 2, so that we don't lose precision in that division by 2. All right. Okay, cool. All right. So let's move on to the next question then. So here's, okay, so 44 is the answer of this one. And then the next question. The next question is not really supposed to be really hard. This one is illustrating a point in the notes of how we can perform rounding, but without using, we can round the result of a division by 2 without having to use floating point division. We can use integer division. We can use integer math the entire time. Even when we need to round the result of division by 2. That is the whole purpose of question number 2, is to illustrate how that can be done. So to answer the second question, we just have to look at what x is, okay, and then plug x into both of these places over here. So we have first 18.13 divided by 10, and we want to round that. So according to what we can do over here, if I'm rounding x divided by 10, I can add 5 to x first, and then divide it by 10, and then take the floor of that. But in C and C++, okay, if you're talking about unsigned integers, then division is by itself, dividing and then taking the floor, because that's the whole point of integer division. So that means we just need to add 5 to this particular value, and then divide the whole thing by 10, and that will give us and then take the floor of that. That will give us 2. And then the other one is just the floor of x divided by 10. And the floor of x divided by 10 in this case is 1, because it's going to be 1.813. The exact result is 1.813 after the division, but because we're taking the floor of that, it becomes a 1. So that means the answer is a 1 in this case, because basically one is rounding up and the other one is taking the floor, which is always going to be less than or equal to the value that we want, that we are taking the floor of. So in this case, the answer is 1. So the purpose of this question is really just to present the method of doing rounding, but without having to make the rule of, if something has a fraction that is 0.5 or more, we round up. If it is less than 0.5, we round down. Instead of specifying that rule, we just say, oh, we can just add 0.5 to the value that we want to round, and then we take the floor of that. It serves the same purpose. But because we're adding 0.5, which is 1/2, right? So if the value that we are trying to round is dividing is the result of division by a divisor that is multiple of a multiple of 2, then we do not need to do any type of actual real number division. We can do everything in integer division, and that's the whole purpose of question number 2, is to illustrate that point. So moving on to question number 3. So in question number 3, and I think this one is, it may be the way I'm asking the question, but it's, a few people have a question about this. So let me just kind of read it. The main idea of converting from base 10 scientific notation to base 2 scientific notation is to change the unit from a power of base 10 to a power of base 2. In other words, the coefficient is specifying how many of the unit that we have. Okay, so in base 10, because we are using 10 to the power of something as the unit, that's the nature of a base 10 scientific notation, is we are specifying the quantity of some power of 10. To answer Martin's question, I'm assuming the square bracket means the floor, right? So if that is the case, that will work as well. If the square bracket of what you put into the text channel represents a floor operation, then that will work just as well. It should work. Okay. All right, so getting back to question number 3, okay. So we are basically changing the unit. So I want to give you a particular value. In this case, x is 4.955 times 10 to the power of -4. And this time we want to change it to be represented by units where each unit is 2 to the power of -22. So what do? It's kind of the same thing as asking, I have an amount, a currency amount of $31.65, okay? But I only got quarters. So now the question is, how many quarters will best represent the value that I just mentioned? And a simple division would do, okay? So we just need to perform a division where this part here is the dividend, and 2 to the power of -22 is our divisor. So, but we do have to be careful because we want the closest. So that means, you want to do a rounding, with the result after the division. Okay, so let's just, take a look at the math of this specific question. So we got this value and then 2 to the power of -22. So I'm just gonna copy this, and we switch back to, oh, I just passed it to the spreadsheet, and I'm going to open a new sheet just for this. So with this one, I can just kind of paste in the whole thing. This is the value, okay, that I want to represent, but I want to represent it in units, where each unit is 2 to the power of -22, like so. So if I just do a division, you can see it is not a whole number, it is not an integer. So that means I need to do a rounding in this case, not the floor, but this time I need a rounding because sometimes it rounds up and other times it rounds down. So the answer is 2078 for this question. So I go back to the browser, 2048 if I remember correctly. Oh, 78. Okay. There we go. So any questions about number 3 then? Okay, no questions. No questions about number 3. All right, so let's save this answer and move on to number 4. And I think number 4 is a little bit harder. because we got two unknowns kind of at the same time. But even with two unknowns, there are restrictions. There are actually two restrictions, right? So when you look at this, it looks like we got two unknowns, but the restriction, there are two inequalities. X has to be greater than or equal to this. X has to be less than or equal to that, less than the other one. So there are actually enough information to figure out what P needs to be, because there are enough restrictions to narrow down the exact value of P. There are many ways to solve this problem. Okay, there are quite a few ways. So I'm going to do it in one specific way. So I'm just going to lock down X to be the minimum of what it can be. Okay, in other words, I just specify X to be 2 to the power of 52 exactly. Then I can solve for P. Whatever P I solve for in that case is the upper bound of the actual integer P, because the P that I solve for when X is the smallest amount is slightly larger than the P that I need. Okay, so if I take the floor of that, I will get the answer right away. Okay, so let's check this out. Let's find out whether this works or not. So we have this amount over here. Okay, before we do this, let me copy and paste the equation, so I can show you how we can solve for that. Okay, I'm copying off the screen so you cannot see this part, but when I'm done copying, I will show you. So V is X times 2 to the power of P, which is the same general equation that I had earlier. Okay, there we go. So now we can see the equation. We want to solve for P given X. So now we say V divided by X is 2 to the power of P. And this is why you can see when X is the minimum of what it can be, that means the P computed, it would be the upper bound of the P value that we actually need. Because when X is smaller, V divided by X, it becomes bigger. All right, so we take the log 2 of both sides. So the log 2 of V divided by X is just going to be P. And we want to take the floor of that because we want our integer P to be to be the integer that is less than or equal to whatever P, irrational P, that we are solving for here. All right, so do we have any questions at this point for number 4? Okay, if not, we can now go ahead and do the actual calculation. And to do that, I also need to figure out what X is supposed to be first. So X is 8.634 times 10 to the power of 21. Okay. Oh, excuse me. There we go. And we already know what X is. X is the minimum of what it can be. So now let's go ahead and solve for that. We have the log in base 2. Oops. Okay. Okay, so we have the log in base 2 of V divided by X. Oh, I misspoke again. This is V and X is this is V divided by X, and X is 2 to the power of 52. All right, so let's review the equation. So the equation is the log 2 of V divided by the smallest value that X can be. So we press the enter key, and that gives us the irrational number. If we take the floor of that, which is 20, that would be the answer for this question. So if I switch back here and enter 20, I think that should be the correct answer. So any questions about number 4? Okay, so what the 20 is telling us is if I have a bit pattern and I needed to fill up the mantissa, remember, in a double precision floating point number has 53 significant digits because we got 52 bits for the fractional part of the base 2 mantissa and then plus the 1 point, so it actually has 53 digits to the whole thing. So whatever mantissa I have at this point, okay, if it has less than that many units, then I need to shift it by p times to the left in order to fill up the entire mantissa space. So in this case, we need to left shift 20 times in order to fill up the whole space. The purpose is slightly different. The other one is to fill up 64 bits, because that's to prepare us for a division by 2. This one is when we are all the way done to the end. We have the mantissa already, but if the mantissa isn't taking up enough space, then we need to make it fill up the whole space, and so that we have the format that we need for double precision floating point number. So the rest of the spaces will be zeros. No, that is not the case because the 52 bits. Okay, so to answer that question, okay, so we can go to the Wikipedia page for double precision floating point number. Okay. All right, so we'll take a look at this thing here. So the 52 bits is the pink part or salmon color part. So that is the fraction of the mantissa. Okay, and we want to fill up this space, by using the fractional part of the mantissa. But the other 12 bits, the remaining 12 bits, 11 of those are needed to specify the biased exponent, and then the most significant bit is the sign of the entire value, whether it is negative or not. Is that okay? So we are not filling up the rest of the spaces using zeros because it is actually useful for other things in the double precision floating point number. So Martin, are we good? Maybe? Okay. So I'm going to continue with the notes. Okay, all right, thank you. All right, so let me go ahead and continue with the notes, and I have no idea where the cursor is on the screen. Oh, there we go. Okay, I just pinged my mouse cursor because sometimes it's hard to find it, especially when you got two screens and you have no idea where I just put where I parked the mouse cursor. All right, so let's go back to the notes. Okay. So, well, before we do that, let me submit the quiz first because I want to make sure that I get full points for the 4 questions that I did answer. Okay. So that one is good, right? Yep. 1 out of 1, 1 out of 1, 1 out of 1, and also 1 out of 1. There we go. And I did not answer question 5 to 8 because they are basically the same as questions 1 to 4, but with different values to test. So there we go. All right, so let's go back to the notes so that we can continue to talk about today's lab, or to talk about specific ideas that you need for today's lab. Now today's lab is a little bit special, so let me talk about the lab first. Then we switch back to talk about the notes, because I need to give you guys a reason, okay, to associate what we are learning today with what I'll be talking about in during the lecture. And plus, I have to talk a little bit about what kind of question I might be asking, so I need to do that as well. All right, so this lab is basically just one gigantic description with a file. No. Okay, it is supposed to have a file submission and not a text area. Okay, so I need to fix that. Let me fix this first, because I don't want anyone to click on it, or if somebody has already clicked on it, I'm gonna have to remove all of those and do it again. And I think that's because I forgot to save it after I made the changes, because I made the changes in another window, and then I forgot to save it after making all the changes. Alrighty, okay. So don't open the lab yet, okay? If you have not opened it, don't open it. If you have opened it already, I'm going to reset it, okay? So just don't start doing anything just yet, okay? All right. So what today's lab is doing is we are trying to figure out how to do the conversion. And Catherine is typing, so I'm going to wait a little bit until she's done typing. I think today's lab has no password, but I could be wrong. Maybe it has a password. But anyway, I'm going to fix it first, okay? So I'll fix it, and then I'll make sure that then I'll give you guys access to it. So maybe the best way to do it is to unpublish it. Okay, let me do that part. Or I can delete it, but can I unpublish? Yep, I can. Okay, now it's unpublished. You guys cannot see it anymore. What you cannot see, you cannot click on. So there we go. All right, so the description for the most part is still applicable. It is just how I want you to turn in, this question is different. So it starts with an archive of the code blocks project. That is the same as what I showed you yesterday. I still have that up, I think. Let me see. Yep, I still have it up here. So this is the project that you're given with this code already. Okay, so the parser to parse a base 10 scientific notation into an unsigned mantissa, which is just an unsigned integer, and a signed integer for the exponent of 10. That part is done already. Okay, so you can start with that. That part is already done. And then the part that you have to do is to run the program, and the objective of your program is to get rid of the exponent of 10 by manipulating the mantissa, and also by changing the exponent of 2. And I'll explain all of that in just a little bit. Okay, and the objective is when your program is done, I want the mantissa to be a 64-bit unsigned integer. It is basically it's taking up as many bits as it can, okay? And I also want exp2, okay, to be a value, so that if I multiply the mantissa to 2 to the power of exponent of 2, it will still be approximately representing the same value that we start off with. So in the example, I'm using 1.23 times 10 times 10 to the power of -10. But when I test your program, I'll test it with a range of exponent of 10, okay, but they will all be negative, okay. So I'm only going to be, this particular program is only responsible to take care of cases where the exponent of 10 is negative, okay. So all right, so there are no questions. Now we can continue to talk about, how do we get this done, okay, from two different perspectives. The first perspective is from the code blocks perspective, okay? Where do I put my code? Your code is going into exp1022.c, and there's only one function over here, okay, which is this function here. The code that I have put here obviously is incorrect for a few obvious reasons. One is it is an infinite loop. Okay, so that's definitely incorrect. Okay, I don't want you guys to turn in a program that has an infinite loop. And when you look at what the program does in the infinite loop, all it does is to increment the mantissa and then decrement the mantissa. It doesn't do a single thing when you look at it from a perspective of what does it do per iteration. So this is definitely the wrong code. Okay, but I'm putting it here just to illustrate how to utilize code blocks. Okay. All right, so in code blocks, when we are going to test this program, you need to go to project, go to set programs argument, and then okay, so I need to, it put the dialog box somewhere else, not in the view of what is being recorded, so now it's good. So we have to go to program arguments, and then we have to specify the switch, which is -n, and then we specify the number that we want to process. So let's say I want to process 1.23 e -10. Okay, that's all you need to do. You click OK, and you can run the program right away. You can go to debug and say start or continue, and the program will run. And it will run to the infinite loop, and then it will be stuck in the infinite loop. Okay, so instead of just running the program, I advise that you put a breakpoint. So to put a breakpoint on the line, you go to the left-hand side of the main text area, but slightly to the right of the line number. This is how you can put a breakpoint. And if you want to remove the breakpoint, it is a toggle. So if you click on the breakpoint again, it disappears. So I'm putting a breakpoint here so that I can stop the program well, not quite stop. I can pause the execution of the program on line 11, so I can kind of check out a few things, at that point. Okay. So do we have any questions about how to use code blocks? At least up to this point. My nose is itchy because I think I got some cat hair. Can we run it so that we see how it works? You mean running the program itself or running code blocks? I'm going to show you guys what happens anyway to get to this point. Yeah, code blocks, no problem. So we go to debug. Okay, so don't use the other. So there are two run buttons. Okay, one is in green and the other one is in red. Use the one that is in red, because if you use the one that is in green, it won't stop at the breakpoint. It will just keep going. So use the one that is in red, or you can just go to the debug menu and then click on start continue, or press the hotkey of F8. Okay, so all of these methods will work, and you can see how the program now has stopped. Now, where it stops can be off a little bit from where the breakpoint is, but it did stop, at the first point that it can stop. And right now I need to move the other window, the other dialog box into view, because it will ask you this question here. I typically just say no. Okay, I don't, I just don't need to save it. So if you want to click yes, that's okay too. but I typically just say no, so I don't have to kind of switch back and forth between the views. So when you add a breakpoint, the breakpoint itself is not the breakpoint, excuse me. The point where the program has stopped is indicated by a yellow triangle. So right now the program has reached line 13, but line 13 has not occurred yet. It is about to execute line 13 at this point. Over here, okay, if you look at here, it is a debugger tab, and it shows you everything that GDB would otherwise show you on the command line. So at this point, you can use any command in GDB. So you can go to Google and look for GDB commands, or you can just kind of use the ones that I have already introduced in this class. Okay, so the first thing you can do is to say, I want to print what is the parameter pn. Okay, and it shows you that pn is a struct number pointer, and this is the address. Now that doesn't show us much, right? So what you can also do is to say, I want to know what is the value of the member Mantissa inside the structure that pn is pointing to. Okay, and it's going to show you exactly that. Okay, we have 123. It is not 1.23 because remember, we want to use only integer math in this entire program. Okay, I don't want to see any double, I don't want to see any float, I don't want to see any power or log or anything like that. I want to only use integer operators, okay, in this entire program. So, so Mantissa is 123, but there's actually a better way to do this. If I want to see everything in the structure the pn is pointing to, I can just say print star pn, and that shows me every single member of the structure that pn is pointing to. So I can see the sign is a 0, the mantissa is 123, the exponent of 10 is -12, which is correct because the original exponent of 10 is -10, but the mantissa was 1.23 at the time. So in order to represent mantissa using an unsigned integer, I can use 123, but if I want the value represented by the mantissa times 10 to the power of exp10, then I have to adjust exp10 or the exponent of 10 and decrease it by 2 because the mantissa is now 100 of what it used to be. It's 100 times of what it used to be. So the exponent has to decrease by 2 to adjust for that. So everything is working, okay? So the parser is already done. By the time your code, which is this particular subroutine, has control, you already have all the parts already separated out for you. The objective of your program is to turn this part into a 0. Okay, this part here, you can use whatever value is appropriate, okay, for exp2, but you also want to have another requirement, which is the mantissa is going to be it's going to have to fill in all 64 bits of the 64-bit integer. Okay, so this way, we are maintaining the best precision, within the operations. So later on, when we need to convert the mantissa back into a 53-bit mantissa, we have to toss away some of the units, okay, toss away some of the bits, but we only toss away bits at the very, very end of the process, not during the process of the conversion. So is that okay? Does everybody understand, how to operate code blocks? Or I should say, are there any questions about operating code blocks? Okay, so we are good here. All right, so now the question is, so how do we, it's an operator. Okay, so pn, okay, so I'm not sure whether type of works here or not, so let me try it. Nope, it does not. There's no type of. It is a pointer to, yes, so the arrow is saying, treat whatever on the left-hand side as a pointer, and then treat whatever is on the right-hand side to be a member of the structure that the left-hand side is pointing to. So let me show you two things, okay? I think this will make it very clear. So if I say pn points to mantissa, it is saying that treat pn as a pointer and treat mantissa as a member of the structure the pn points to. Okay, and obviously this works because we did it before already. But at the same time, I have an alternative syntax to do exactly the same thing, which is go to pn first and say, I don't want the pointer, I want what it points to. But you would recall that this is going to say, oh, we want the entire structure. Wait, nope, nope, nope. This is the entire structure, but of the entire structure, I just want mantissa. That works too. So these two expressions are exactly the same in C and C++. Using the arrow notation is what most people do, but it really boils down to exactly the same thing as dereferencing the pointer first to get to the structure. Then you use a member of operator, the dot operator, to access a specific member of the entire structure. So either way works, and either way still requires an understanding of what is a pointer and what is dereferencing. And that partially is why we need C or C++ as a prerequisite of this class, because Java does not have this kind of concept. Java does not have pointers, it does not have dereference, it just has its own way of handling quote-unquote pointers, which we call references in Java. All right, so are we good so far with kind of how to operate code blocks? So I just want to remind everybody, I'm just nagging here, that you have to go to project and set programs arguments. So you have to remember to change that first. Okay, I'm going to pull that screen into where you can see it. So you have to make sure that whatever number you want to process is in the program arguments, and it's not just by itself, it has to be a -n and then that number. Okay, now, it seems to be making the program more complicated than it needs to be, but this way, when you run this program stand alone as an executable, you can then specify -n, whatever number you want to utilize on the command line, and the program will take that as part of its arguments. So this is how we can specify switches and arguments to a command line program, is through the program arguments. So, and for those of you who are curious of how that is processed, you can go to main. It shows you the logic of how arguments are processed. And for those of you who are curious of how parsing is done, so that we can actually extract the mantissa and also the exponent of 10, you can go to parse. Okay, this is a function that I wrote. It's a fairly simple function that does all the parsing. That extracts the different parts of a floating point number. It has a bunch of little helper functions up here to help kind of break out the individual parts of that thing. So if you want to read this part, that's fine too, but do not change. Okay, do not change anything in main or parse. Okay, the only code you're supposed to change is in this file. Some of you probably will recognize and go like, hey, there's one thing I need to do again and again and again. Can I write my own subroutine? The answer is yes. Okay, so you can write your own helper subroutine and put it into the same file, which is exp1022. So this way you can structure your code a little bit better. This is not going to be a long program. Okay, I can tell you right away. Okay, you're not going to need any more than, I think, maybe 20-25 lines at the most. Okay, so it's not going to be a complex program. So whether you turn parts of it into a subroutine or not, that's entirely up to you. It is probably not necessary. So are we good so far? Are we ready to talk about how to turn that exponent of 10 from a negative integer to 0? All right. So looks like we're good at this point. Yes? Okay, all right. So in that case, I am going to switch back to the class notes and take a look at how that can be done. So I'm switching back to the main list of modules, and go back to the module that we were in prior to today's lecture. And I just remembered one thing that I said I would do is to kind of give you another idea of what kind of question you might encounter in tomorrow's test. So let's do that one first, because I definitely don't want to forget to do that. All right, so let's talk about base conversion. Okay, so this is a little bit different. I'm talking about tomorrow's exam one, but I think it is kind of a good idea to give you some idea of what kind of question I might be asking. So I might ask you a question where it is a base conversion question. Okay, so typically a base conversion question is not exactly difficult. Okay, and there are online calculators that can do that, right? I personally have not searched for that nor used it, because I can always do it by hand and do it myself, but I know some people have found those resources already, which is okay, because I did say that you can use any online resources as long as it does not involve collaboration. Okay. Now, collaboration in the wide sense, means that even if someone took the test at 9 o'clock and that person sends a copy of the test to a person who's going to take it at 9 p.m., that is still considered collaboration. Okay, so do not disclose the content of the test to somebody else in the class, because that is considered collaboration as well. Okay, and I will look at that as a case of cheating. So don't talk to anyone about the test tomorrow. Now, after tomorrow, hey, you guys can talk about it all you want, and I'll be talking about it too, because I want to give you the solution on Thursday. Okay, but don't talk about the test with anyone else tomorrow, even if you are fairly sure the other person has taken the test already, because you never really know, right? So, all right, so once we got that out of the way, let's talk about the base conversion. So if I want to convert from base 10 to base, let's say 7 again, okay, it's not really too difficult. Okay, there's one equation in my notes that can convert to a single digit in a different base, but that means you kind of have to reapply that equation several times to convert the entire thing. So let's say I want to convert 1000 to 7, okay, to base 7. So what I can do is I can do division. Okay, this is kind of a short way to do this division. So I can divide 1000 by 7. Okay, I got 1 over here, I got 4 over here, and I got 2 over here with a remainder of 6. Then I divide it by 7 again. 14 divided by 7 is 2. 2 divided by 7 is a 0 with a remainder of 2. 20 divided by 7 is a 2 with a remainder of 6. And 2 is less than 7, so I don't need to try again. So now that we have all these digits, how do we read this, right? This is digit 0, this is digit 1, digit 2, and this is digit 3. We only need 4 digits in base 7 to represent 1000. So in base 7, 1000 in base 10 is 2626. Now that is just coincidental. Okay, I just pulled 1000 out of thin air, and I also pulled 7, which is the new base, also out of thin air. It just so happens that we got a kind of interesting pattern here. Okay, 2626 in base 7 is representing what we know as 1000 in base 10. So is that okay so far? Okay, so now the question is, well, how can I ask you a question about base conversion when people can just go online and do the base conversion without knowing how it is done because they found a website to do it? So the question that I might ask you is going to involve something like this. It might have a missing digit here and say a missing digit over here. So I will replace those digits with a question mark over here and a question mark over here, and you need to figure out what value can fit into those question marks. All right. So this is one form of question that you may encounter tomorrow. Is I give you two numbers in two different bases, and each one has one missing piece. But we know that the two numbers in two different bases are really representing the same value. So what you need to do is to figure out what digits can fit into those places, okay, the placeholders. One is here and one is over here, so that the numbers, are now representing exactly the same value. Is that okay? All right. So I'm gonna let you guys think about this a little bit, okay? Because I'm gonna be online with you guys until about 1 o'clock, right? So I want you guys to think about this a little bit first, because I don't want to give you the solution, right? Because if I give you the solution right away, you won't have a chance to think about it. It is your thinking about this problem that is going to help you understand the mechanism, and the concepts involved in base conversion. So I don't want to give you the solution right away, okay? Because that's not going to be helpful. I want you to think about it a little bit. When I say a little bit, I really mean about half an hour, maybe even to an hour. Okay, you kind of have to chew on it for a little bit, okay, and really go deep to understand, okay, what is a number? How do I get the value that the number is representing? And what are these missing pieces over here? What can fit into these missing pieces? Now remember, in the test, you can use spreadsheets. Okay, you can go use Google Sheet if you want to. Okay, I personally like Google Sheet because it just saves right away. But in the test, you don't need to save the spreadsheet. So you can use Excel, you can use LibreOffice. Those are very, very useful tools, because if you want to test, I know this digit can only go from 0 to 6. Oh, I know the other digit can only go from 0 to 9. A spreadsheet allows you to play with different values really quickly, so that you can kind of you can take a visual glance at the numbers in the spreadsheet and quickly find out the pattern, and then say, oh, okay, I think I got it. These two match up, okay? So I'm gonna leave that out a little bit, but I don't want to bring this up. This is the sort of I don't want to call it a twist, but this is the sort of modification that I would put into a typical problem that we have solved in the lab, just so that it is still testing your knowledge and your understanding of the concepts of the same thing, okay, but it involves problem solving in the process that, as far as I know, no internet site nor calculator can do this directly. Okay, so this is how I want to kind of structure the test. All right, and Catherine is typing. I'm gonna wait until I address that before we move on. Okay. Oh, okay, so it shows up here. Interesting. All right. Hopefully we can. Yep, and that's why you don't want to be tired, okay? Because you need your mind needs to be sharp in order to solve problems. This is not about memorization. This is not about how much stuff can you cram into your mind. This is about how quickly you can apply what you have learned to solve problems. All right, so let's continue to talk about how base conversion. Okay, I mean, it is base conversion, but we're converting scientific notation from base 10 to base 2 now. Okay, so we'll start with something that cannot be done, not easily. So we'll start with 1.23 times 10 to the power of 40. Okay, so this is a pretty small number. Okay, it's a pretty small number, and we know the program that I just gave you will break this up into 123 as the mantissa m times 10 to the power of negative 42 this time, because remember, because the mantissa was 1.23 and it is now 123, in order for this to be the same value as this, I need to change the exponent of 10 so that it is now 2 less than what it used to be. So now v is the same again. So this is the exponent of 10, and I'm just going to put in the 2 over here to the power of 0. So once again, okay, we mentioned this yesterday already. Well, 2 to the power of 0 doesn't seem to do a single thing because it's just 1. You're absolutely correct, but we are going to change it eventually. So now the question is, okay, what can I do to change this 10 to the power of negative 42 to 0? Well, don't expect to do it all, jump from negative 42 to 0 in one single step, okay? Because the whole idea is we're going to set up some loops here so that each loop, okay, or each iteration of a loop only, okay? In other words, what can I do here so that the exponent of 10 is to the power of negative 41? Okay, because that's progress, right? Because negative 41 is one step closer to 0 compared to negative 42. So it is progress. What do we need to do here? Well, the power of 2 doesn't seem to do anything to that, right? So by incrementing the power of 10, that means I have to change the mantissa. So now we have to say, well, this is what we need to do. Oh, but that's not good, right? Because remember, I want this entire program to only use integer arithmetics, okay? And 12.3 is not something that we can represent using an integer. So that's not going to work, okay? Cross this out. What can we do then? Well, maybe what we can do is to make the mantissa larger, okay? So we can say 246. Change the mantissa to 246. Keep the power of the exponent of 10, but this time because I just doubled the mantissa, so now we have to change the power of 2 or the exponent of 2. So that is now to the power of negative 1. Is that okay? By doubling the mantissa, I have to decrement the exponent of 2. Is that good? Is the math of this doing okay? All right, cool. And of course, there's no, I don't need to stop here, right? I can keep going. I can say, oh, by the way, I can also double this, so it becomes 249 times 10 to the power of negative 42. But this time, I have to decrement the exponent of 2 again, so it's now to the power of negative 2, and so on. Okay? And you can see this approach at some point is going to hit a limit. In other words, if I keep doubling the mantissa, at some point it's going to use up all 64 bits. And when it does, I cannot double it anymore. Does it make sense? Okay. So at some point, okay, this is going to be huge. Okay, this is going to be a huge number here. The power of 10 is still to 10 is still to the power of negative 42, but then the 2 is going to be to the power of, because each time I left shift, I have to decrement the exponent of 2 by 1, which relates to the lab that we just did yesterday. So at some point, it's going to be a number here. I cannot tell you right away what it is because I don't know. Okay, but your program will. Your program, because it's going to be in a loop, doubling, but every time it doubles, it will also say, oh, okay, gotcha. Not anymore. I just scrolled it. I just have to remember not to write in that particular area. Okay, so I need to figure out what this is and also what this is, but both are determined by how many times I need to left shift the mantissa, right? So that is in the instruction of the in here. So what we are doing is we are now converting from base 10 scientific notation to double. And we already talked about how to get rid of the decimal point of the mantissa. Okay, we just turned the entire mantissa into an integer and do some adjustment to the exponent of 10, and we are all good. And now we are talking about how to get rid of the exponent of 10. We break it up into two different cases. Is, what if the exponent of 10 was originally less than 0, which is the case that we want to deal with. So what we want to do, okay, I'm skipping a little bit here. So what we want to do is to double the mantissa and then decrement the exponent of 2 and keep doing this until we say, whoa, don't do this anymore, because if I do it one more step, one more time, I'm going to exceed what a 64-bit integer can represent. Okay? Once we have the mantissa being that huge, gigantic 64-bit number, actually using up all 64 bits, okay? Then it's time to say, well, what we can do now is to divide that huge, gigantic mantissa by 10. But if you just divide something by 10 using integer division, every single time you do that, you're losing some value, because in integer division, it's always taking the floor. If you're always taking the floor, which is, the result is slightly smaller than what it should be, then if all the errors are leaning in one direction, then we have what is called a bias. Okay, so you have you don't just have an error, but your error has a bias. And as a result of the bias, feeding back to itself, the actual end result that you end up with is going to be quite a bit smaller than what it is supposed to be. So a biased error itself is not good to begin with, but a biased error is really bad. Okay, so we don't want that. And what we want is rounding, and the mechanism of y plus 5 divided by 10 instead of just divided by 10 is doing the rounding. The math of that is actually mentioned over here. So you want to read this section if you want to know why it works. So, but I'm kind of skipping a little bit ahead because I want to give you an idea of what your program is supposed to do. So you do this in the loop until m cannot double any further. Then you perform this step here. But since you're basically dividing the mantissa by 10, that means your exponent of 10 can now increment by 1 so that the value being represented is preserved. This is how you perform one step to change the exponent of 10 so that it is one step closer to 0. So what do you do after you do this? Okay. Now, after you do this, if E10 is a 0, hey, you're all done. Cool. On the other hand, if E10 is still negative, then you have to go for another iteration by maximizing m first, and every time you double m, you have to decrement E2 by 1, and after you can no longer double m, then you go back to this step here and use the rounded method to divide the mantissa by 10, increment E10 by 1, and then check again to see if E10 is now a 0. So are we okay with this process? Yes, no, maybe? Okay, so let me work on this one, using a much smaller, I should say narrower bit width, okay, because 64-bit is a lot, okay, because if you want to write out a 64-bit number in base 10, it's going to take up 19 base 10 digits. That's a lot, okay. So what we want to do is to say, what if we're dealing with let's say 16-bit numbers, okay, that I think that's manageable. Yeah, there'll be a double loop. Well, you don't need a double loop, but the double loop is probably the same way of writing this program, but there's a different way to write this program without using a loop. But I would call that method less sane. Okay, it still works, so I cannot call it insane, but it's not intuitive. Okay, so let's work on this by hand, and using only 16-bit integers. Okay, so we want to use 16 bits only, and so we can do this. All right, so next step, go back to my spreadsheet over here. Okay, so this time, I'm going to use 16-bit integers, 16-bit unsigned for M. Okay, so excuse me. And we'll start with this. Okay, so we have 123 times 10 to the power of negative 42 times 2 to the power of 0. This is where we start. So we'll work with doubling m for until we cannot double it any further. Okay, so I'm gonna use. I'll show you how we can do this. Okay, so I'm gonna use a terminal. Well, I think a spreadsheet works better in this case, so I'm going to go back to the spreadsheet. So where's my spreadsheet? Down there. There we go. Okay, so I'm going to open up another tab so I can this is our x. Okay, x is 123, and we want to keep doubling it until it can no longer fit, until it barely fits. Okay, I should say until it barely fits within the 16-bit unsigned integer. Okay, so let's see how many times we need to do this. Okay, so p is 1. Okay, so this is p. When p is 1, then we have 123, which is this number, times 2, right? And when p increments, okay, I use the term p because that's the term that we used in the previous lab. So I just want to correlate what we're doing here with concepts that were introduced in yesterday's lab. And this is going to be double the value from before, like so. Okay. So now we just keep doing this. I forgot the doubling. Yep, it needs to be B2 in this case. All right, so now we can just kind of keep scroll this down and go like, whoa, okay, at some point, we are going to exceed it, right? So let's check out which one is exceeding. With 16 bits, we can represent all the way up to 65,535, okay? And we can see that, oh, this is the last one, right? Because this value doesn't fit into a 16-bit unsigned integer anymore. So the first question that you kind of have to ask yourself, and the answer is actually somewhere in the notes too, is what condition will tell you and say that, oh, don't do this anymore. If we do this doubling anymore, we're gonna exceed what a 16-bit integer can represent in this case. Okay, so I'm gonna leave the math of that condition up to you guys, because you can also read in the notes over here, and it says right here, as long as, okay, now this is really just another way to say while, right? Because while is really saying the same thing as long as m is less than or equal to the largest numerator value, which is basically in this case 65,535 minus 5 divided by 2, because the idea is if I double this, it's gonna hit, because I need a plus 5 over here, so I need to leave enough room to do the plus 5, and therefore I need to do a subtraction by 5 here. Okay, so you kind of have to look at this sentence here and turn it into a loop and the condition of the loop. Okay, so what I'm really saying is this is a loop, okay, but you have to translate it into C code loop. The logic is here already. Okay, so getting back to here. So now, okay, I take this value and say, okay, this is the last value of m. So what do? I have to look at how many times I did the shift. Now for each iteration of doubling, you can also change E2. So in this particular example, okay, E2, if I want to use E2 as a column, E2 itself starts with a value of was it 0 to begin with, and every time I double x, I have to decrement E2 by 1. So this would be the previous value minus 1, and as a result, when I'm going to extend it with the same for the same length, but on this particular row, when m becomes 62,976, e would be -9 at this point. And then what do? We now say, well, this is the best we can do. Okay, we have to do the division by 10 at some point, right? So this is the best we can do, because if we do a division by 10 when m is only 123, we lose a lot of precision. Okay, because 123 divided by 10 is 12, because integer division automatically drops the fractional part. So if you think about the 0.3 out of 12, that is approximately what, 2 point something percent. Okay, 2 point something percent is actually pretty excessive. That's a lot. On the other hand, if you take this number here and you divide it by 10 and you say, okay, how much precision am I losing? Well, what do you think? Well, if you just take this value without doing the rounding, you would end up losing the 0.6, but it's out of 6,000 something. So if you lose 0.6 out of 6,000 something, the actual percentage of the error is much smaller. So I'm just kind of guessing in my head right now, what the actual percentage is going to be. So I think that's what, 0.1%. So instead of having 2%-ish, we only have 0.1%, which is much better, right? And this is the reason why we are maximizing the mantissa to fill it up, to the entire width of the unsigned integer before we divide it by 10, because then what we are losing is going to be a lot smaller. So now over here, we'll say, okay, what about the new m? The new m is going to be this value. Okay, it's already the largest value we can fit into 16 bits in this case. Remember, we have to add 5 to it first before we divide it by 10. So we now say take this and add 5 first, and then divide it by 10. In C, that's already good. Okay, plus 5 divide by 10, we're good. But in the spreadsheet, I have to take the floor function, because otherwise it'll give me something point something, right? So I have to use a floor function for this purpose in the spreadsheet. So this is my new m. And what about my new E10? My old E10 was -42. So now, because I just divided the mantissa by 10, I can now increment the exponent of 10 by 1, so it is now -41. Is everybody still following the math involved? Are we good so far? Because this is one, okay, very good. So this is basically one iteration of the outer loop. Okay, so by the end of one iteration of the outer loop, I would have the exponent of 10 increased by 1. Okay, we are now one step closer to what we want to be at, which is 0. Okay, so what do we do next? Well, what we're going to do next is to plug this m back into here, repeat this process, maximize it, figure out how many times we have to do it, change E2 accordingly, and then divide m by 10 again, increment E10 by 1, test it, and then if we need to, we go back again. All right. Yes, so let's go for another loop here. I'm just thinking about whether, okay, let's do it this way. I'm keeping everything that we have here. Okay. And column F is not actually being used, so let's hide it so it doesn't take up any space. Okay, we are already out of time. Okay, but I'm just using the lab time to do this part, which is appropriate because this is actually your lab. So the new E2 is whatever we have here, which is -9. Now remember, this is all based on only using 16-bit unsigned integers. So your program is going to be using 64-bit unsigned integers. So these numbers won't be exactly the same, but the approach should be about the same. All right, so now we use a column J to restart the whole thing. So we look at M again. So this time M start with 6298. We look at how we adjust E2. We can adjust both at the same time. Okay, so we can say this E2 is the same as this one here. And then we do the doubling of the M and decrement the E2 until we cannot do it anymore. So we look at this and say this is 2 times the previous row, and this is the previous row minus 1. Okay, and then we just keep doing this a few times, and I'm going to show you a lot more steps than it needs, okay, but you get the idea, right? By this time, this is the last value of M before it goes over what we can represent as a 16-bit unsigned integer. So this is the row that we're going to pick. Okay, I'm just going to highlight it so that it's clear which one we're picking over here, and I'm going to highlight this one so that we can tell which one we are using over here. Okay, so we look at this and then we say, well, this is the best we can do. Okay, I can only make M as large as this before we do the division by 10. So now we say, what is the new M? The new M is, oops, wrong key, is once again in parentheses this value plus 5. Now this is why when we check whether it's time to exit the loop, we have to make sure there's room for another plus 5, because of this. So it is this value plus 5, the whole thing divided by 10. Oops. And then we have to take the floor. The only reason why we have to specify a floor in this case is because in a spreadsheet it does not know what is integer division, but in your program integer division is the only thing that you can do. So the new M is 5038. The new E10 is going to increment the old E10 by 1, so it's now negative 4040. And then your new E2 is negative 12. Is that okay? So now we have gone through 2 iterations of the outer loop. And as a result, E10 went from negative 42 to negative 41, then to negative 40. How do we know whether we need to go back again? Yep, we keep doing it until E10 is 0. But you don't want to use a do while loop because I might give you a value where E10 is 0 to begin with. So do it with a while loop that says, okay, that says, if E10 is not done yet, okay, get into the loop. Any other questions? All right. Okay, so if there are no questions, I'm going to turn off the live stream, and you guys can start to work on the program. Oh, before we leave, okay, before we go, okay, it is kind of important that I fix the lab first, okay. And I thought I fixed it, but I obviously did not. The due date of this lab is on Friday. Okay, I want to point it out because don't try to get this done in 1 hour and a half. Okay, that is not the intention. Okay, Martin has a point here. If we have limited space for the mantissa, then how can we keep looping? Because every time you divide the mantissa by 10, then you got room again for more multiplications by 2. I can share the spreadsheet. That's not a problem. I can share the spreadsheet and also the journal for today, because I think the spreadsheet is going to be helpful because we can see how M got to as big as it can that barely fits within 16-bit, but because we divide it by 10, well, okay, we add 5, then we divide it by 10, now it is only 6,000 something, which means I get to multiply it by 2 a few times before I hit the limit again, and then I divide it by 10 again, and then I keep multiplying by 2, and I divide it by 10, then I keep multiplying by 2, and then we divide it by 10. So yeah, okay, very good. So the idea is we are trading, okay? We are trading E10 using E2. We are trying to get rid of E10 by saying, okay, to compensate for getting rid of E10, we adjust E2 as well as M itself. But we want to be basically we want to be representing the same value the entire time. Just one more thing before we go. How do you know whether your program is working or not, right? So I want to show you this part here, okay? Because the value being represented should still be the same. So what is the value being represented? The value being represented is the mantissa times 10 to the power of E10 times 2 to the power of E2, which is like that. So if I press the enter key, I'd better see 1.23e negative 40. Yes, okay? And after all of these gyrations, okay, after I do all the gymnastics, I should still end up with the same value being represented over here. So if I just copy this formula to here, because I think the positioning of M, E10, and E2 are the same, so copy and paste will work. You can see that I have about the same value. I already lost some precision because 16-bit doesn't give me as much precision as I need in order to preserve the value enough that it shows up to be the same. But you can see how this is already losing some of the precision because I'm using a 16-bit number for the mantissa. So this is how you can check whether your program works or not. Is for after each iteration on using GDB on the command line of GDB, you can do this part here. And I think power may be accessible in GDB. I may be wrong about that. But you can always plug the value into a spreadsheet outside of GDB to test it. And the spreadsheet that I just showed you, this is how we can test it. So if GDB does not let you use power, don't use the caret. Okay, caret means bitwise not, exclusive OR in C and C++. So caret doesn't mean to the power of in GDB. So don't use the caret. If power doesn't work, then you have to take the values from GDB to a spreadsheet and do the calculation. But the idea of doing the calculation this way, this equation here, this formula, is how you can check your program and see whether it is working or not. Okay. Any other questions before I turn off today's live session? So once again, this one is due on Friday. Okay, I know you guys have to spend some time to prepare for the exam tomorrow, and you probably don't want to do this tomorrow, okay? But we still got Thursday and the entire Thursday, and to some people, a good portion of tomorrow to work on this program. So we got some time, so don't rush it, okay? Just work on it slowly, understand the concepts first before you rewrite the code. Yes, so Catherine, you are correct. I will send you the link to the shared document. It will be going to your apps.losreels.edu Gmail account, and as soon as you get that link, you can get started with the test. And about an hour and 20 minutes after, that link will, the document will be unshared. I'm just waiting for Catherine's typing. Yes, so you're going to write your answer in the document. There's no official submitting to do because it's automatic. what I'm going to do is my script will automatically um, unshare the document after an hour and 20 minutes. It's going to be a little bit more than that, but I don't want people to really push too hard, because you might get maybe a few seconds after that, depending on where you are on the list of people. Um, but the document will basically just become unshared at some point, and then I have a table, so I know which document belongs to whom. So I will basically, when I grade it, I know whose exam I'm grading. Alrighty. And I think Catherine is still typing something, so I'm gonna wait for that before I turn off the live stream. All right. Oh, okay. All right, cool. All right, so I think we're good today, and I'm going to share today's journal, which also has a whole bunch of other days in it. You just have to go all the way to the end. Oh, Mertessa is typing. Let me save the spreadsheet and then save it. Oop. What did I do? I think I know what I did. I'm now sharing the entire desktop on my laptop computer, which is okay, because all I want to do is to share the document. So let me save the document first. And then upload to today's lecture, and I'll pin it too, so this way all the files uploaded can be easily located. And then we need to get to journal and make sure I save it first and then upload it. Okay, Mertas, okay, so Mertessa, if you mark times, when you mark time slots, those are the time slots that you are saying you are not available. All right? So if you think you marked it incorrectly, because I only want you to mark the time slots that you are not available. So if you accidentally marked the time slots that you are available, then go ahead and change it, because you can still go into the form and change what you submitted. And the first time slot that you are available is the time slot that you're assigned to take the test. Is that okay? All right. Okay, so I just uploaded the journal file as well. Oh, the lab is not it's not adjusted yet. That's why it's not published yet. So I'm gonna have to adjust the instruction, because I'm changing the way it's done compared to last year's project. It's still the same nature, but the way how you turn it in is slightly different. So I'm gonna adjust that first before I release it, before I publish it. So give me a second to do it. I'm gonna stay on the live channel for this part, just so that you guys will know right away when I'm done editing it. You won't see the actual editing, but when I'm done, you'll know. All right, so I'm changing it from an essay question. You probably won't see it anyway. So I'm changing it from that format to a file upload question. There we go. And I'm just checking the due date. Due date is correct. It does not need an access code. Okay, so this one does not need the access code. And I just clicked the save and publish button. So you guys should see it now. All right. All right, so I think most people have left the live stream anyway, so I'm going to stop the live stream now. But I'll go away for about 10 minutes and then I'll be back to answer questions.